Hello, my name is Ashley Blackwell, and for my presentation today, I will be giving you an overview of my specialization project to date. This project is being completed for the Specialization Project Data 675-9040 course under the guidance of Professor Dr. John McKeeby. I welcome any and all feedback, as it is valuable for me to complete this project in the most effective and, in the future, hopefully helpful way that I can. The core problem that I am analyzing is whether a convolutional neural network can accurately classify chest CT scans into 4 different categories. The categories being adenocarcinoma, large cell carcinoma, squamous cell carcinoma, and benign tissue. In my words, this problem matters because lung cancer remains the leading cause of cancer deaths worldwide, and early detection is critical for survival. At the same time, radiologists also face heavy workloads, increasing the risk of misdiagnoses or delayed diagnoses. By applying AI, in this case, convolutional neural networks, the goal is not to replace the radiologist, but to support them by improving efficiency and accuracy in identifying cancerous tissues within CT scans. Chest CT scans are inherently difficult and time-consuming to interpret, and radiologists are under significant workload pressures. This increases the chance of missed or delayed diagnoses. Another challenge is that lung cancer subtypes, like the adenocarcinoma, large cell carcinoma, and squamous cell carcinoma, often look very similar on CT scans. This visual similarity contributes to variability in diagnosis and makes automated classification very difficult. From a data perspective, the dataset itself is very imbalanced. There are far fewer images of large cell carcinoma at 5,000 compared to the other classes, which poses challenges for machine learning models that rely on balanced data. Finally, misclassification carries serious clinical risk. A false negative could delay critical treatment, while a false positive could create unnecessary anxiety, stress, and follow-up testing for patients and family members. That's why improving accuracy in this context is so important. Lung cancer is the leading cause of cancer-related deaths worldwide. Early detection is one of the strongest predictors of survival, so improving diagnostic speed and accuracy directly impacts patient outcomes. At the same time, radiologists face heavy workloads, and diagnostic interpretation can vary across individuals. This can lead to delays and sometimes inconsistent or inconclusive results. A convolutional neural network can serve as a decision support system to improve efficiency, consistency, and reproducibility in lung cancer screening. By standardizing the way images are analyzed, convolutional neural networks can help reduce variability between human interpretations. Finally, reducing false negatives is especially critical in this context. Missing a cancer diagnosis has far greater clinical consequences than a false positive, because delayed treatment significantly reduces survival chances. For this project, the scope is focused on the technical research and experimentation side of machine learning, not on clinical deployment. In scope, the project includes acquiring the dataset from Kaggle, performing exploratory data analysis to check for imbalances, applying pre-processing steps such as resizing, normalization, and augmentation, and then I'll build a convolutional neural network from scratch and compare it with pre-trained models using transfer learning. The training and evaluation will focus on classification metrics such as recall, F1 score, PRAUC, and confusion matrix. For explainability, I will apply GradCam visualizations to ensure that the model is learning from the correct regions of the lung, and I will carefully document all steps to ensure reproducibility. What's out of scope is equally as important. This project does not attempt clinical deployment or integration with hospital systems. It also does not include multi-site trials or patient-level longitudinal analysis. which would require access to private medical data. Advanced generative modeling and regulatory or ethical approvals, such as HIPAA or IRB, are also outside the scope of this course project. The dataset for this project was compiled by Mohammed Haney and has been publicly available on Kaggle since 2020. It contains the chest CT scans that were labeled by radiologists. Each row in the dataset corresponds to a single CT scan image. The images are grayscale with pixel intensity values ranging from 0 to 255. Each image is labeled with one of four classes: the adenocarcinoma, large cell carcinoma, squamous cell carcinoma, and benign or normal tissue. The dataset contains about 25,000 images in total, with roughly 8,000 of those being the adenocarcinoma images, 5,000 the large cell carcinoma images, 6,000 of the squamous cell carcinoma images, and 6,000 of the benign tissue or normal tissue. The image sizes are not uniform. They range from 200 by 200 pixels up to 512 by 512 pixels. And there are some outliers, such as very small or corrupted images found within the dataset as well. For training and evaluation, the dataset is split into 70% training, 20% validation, and 10% testing. During the exploratory data analysis, several challenges have been identified. First, the dataset is imbalanced, with large cell carcinoma underrepresented at about 5,000 images. This imbalance risks biasing the model toward the majority class. Second, the image size and resolution vary significantly, from 200 by 200 pixels up to 512 by 512 pixels. To manage this, the images will be standardized to approximately 224 by 224 pixels for consistent model input. Third, pixel intensity values span from 0 to 255 in grayscale. These will need normalization, either to a 0 to 1 or a negative 1 to 1 scale, to stabilize training and prevent exploding gradients. Finally, some low-quality or corrupted images are present, and the dataset contains only slice-level images without demographic context. This does limit generalizability across populations and scanners, so quality filtering and clear documentation will be essential. The methodology follows a structured pipeline. First, the dataset is acquired from Kaggle, followed by pre-processing, which includes checking class sizes, resizing images, normalizing pixel values, and generating augmented images. Next, I will build a baseline CNN with layers such as convolution, max pooling, dropout, and dense layers. I'll then extend this with transfer learning using pre-trained models like ResNet 50 and EfficientNet to improve performance. Hyperparameters, including learning rate, batch size, dropout, and optimizer, will be tuned for optimization. For the training and evaluation, I'll measure recall, F1 score, PRAUC, and confusion matrix. For explainability, I will apply GradCam to confirm the model is focusing on the correct lung regions, and perform error analysis to understand misclassifications. Visualizations will ensure the model emphasizes clinically relevant areas, not artifacts. Finally, reproducibility will be supported by detailed logging, notebooks, training logs, and proper APA references for datasets and methods. In medical AI projects, explainability is critical. To achieve this, I will apply GradCam overlays to test images, ensuring that the model is focusing on the correct lung regions rather than irrelevant artifacts. In terms of error focus, I'll prioritize false negatives since missing a cancer diagnosis carries the highest clinical risk. Finally, I'll perform an audit by stratifying errors by class and confidence levels. This structured error analysis will help identify whether mistakes are systematic or are tied to rare cases. Every machine learning project carries risk, and this one is no exception. First, bias. Since this data set may not generalize globally, I'll document findings carefully and, where possible, test again against additional subsets. Second is overfitting. I'll use regularization and early stopping to avoid the model simply memorizing the training data. Third is data leakage. Strict control of training, validation, and test splits will prevent augmented images or labels from leaking between sets. And finally, label noise. Radiologist variability is unavoidable, so I'll rely on robust training methods that can tolerate noisy labels. These mitigations will help make the model's results more trustworthy. For my work completed thus far, I started with Unit 1. In Unit 1, I framed the problem, I selected the data set, defined the machine learning objective, and outlined the full pipeline from acquisition through deployment. In Unit 2, I narrowed the scope. I defined the specific research problem and clarified both the importance and the limits of what I can realistically achieve with this project. In Unit 3, I conducted exploratory data analysis and profiling. That meant documenting class counts, image sizes, variability, and outliers, and building a data dictionary. This step was critical because it surfaced the imbalance and inconsistencies in the dataset. And finally, in Unit 4, I prepared for this presentation, establishing visualization standards, creating the outline, and working with peers for critiques. Altogether, these steps have created a strong, reproducible foundation for the modeling phase. Looking forward, Unit 5 will focus on visualizations. I'll finalize and present 2 publication quality charts from my EDA and continue building the CNN baseline. In Unit 6, I'll extend the modeling work, refining the CNN and experimenting with transfer learning to improve performance. Unit 7 is where predictive modeling and evaluation come together. I'll train the models, evaluate with recall, F1, and PRAUC, and then apply GradCam to interpret the results. And finally, in Unit 8, I'll bring everything together in the final report, summarizing results, documenting methods, and reflecting on what the project achieved and what limitations remain. From the early stages of this project, several key lessons stand out. First, careful problem definition and scoping were essential before touching the data. They set the guardrails for the entire workflow. Second, class imbalance emerged as a major challenge, particularly with fewer large cell carcinoma cases at 5,000 images. That means I'll need augmentation or class weighting to train a fair model. Third, exploratory data analysis revealed significant variability in image sizes, reinforcing the need for consistent pre-processing. Fourth, reproducibility and documentation are not just academic requirements. They are what will make the project reliable and transparent, from data splits to pre-processing choices. And finally, visualization principles matter. By applying self-contained chart design, maximizing data-to-ink ratio, and using an accessible color scheme like blue, orange, and green, I can make the results interpretable not just for myself, but for my peers and reviewers. And this wraps up the presentation of the specialization project that I am doing thus far in the specialization project course. And here are the references. The references have been used to work on the project and to compile this presentation and have to do with this presentation specifically. I have enjoyed doing this and will enjoy. I cannot wait to see what comes. Thank you so much for listening.